Hello everyone, in this video I'll take you through how to do hypothesis testing on the regression coefficient estimates beta 1 and beta 2. Right, so this table is very useful and also very familiar to you. It's very similar to a table you saw in Appendix A that lays out the same 5 steps that you were introduced to in Appendix A, where step 1 involves you stating 2 hypotheses, a null hypothesis as well as an alternative hypothesis. You then in step 2 compute a test statistic given by this relation over here. Each case is the same. You look up a critical value in the t distribution table. You then compare the value, the critical value, to the test statistic, and then to see which one is larger than which, or in other words, to see whether the test statistic lies within the acceptance or rejection region of the sampling distribution. And then finally, you draw a conclusion based on that comparison as to whether the null hypothesis is rejected or not. That's looking at the rows table. Looking at the columns, we see 3 types of tests: a two-sided test, a right-tailed test, a left-tailed test. In the case of a two-sided test, the thing that differs in step 1 for these tests is that the alternative hypotheses are stated differently, right? That's the only thing that differs in step 1. The null hypothesis in each case is stated with an equality between the true beta 2, and the same process follows for beta 1, between the true parameter and the hypothesized value of the parameter. In the case of a two-sided test, the alternative hypothesis is stated as beta 2 or beta 1, not equal to the hypothesized value for beta 2 or beta 1. You specify an alternative hypothesis in that way if you are indifferent to whether the true beta 2 is larger than or less than the hypothesized value, right? So in that case, you're really just interested in whether beta 2 is exactly equal to a given number. But you're not so much you're somewhat indifferent to the direction in which it might be wrong. For a right-tailed test, on the other hand, where you have a larger than sign between the true beta 2 and the hypothesized value for beta 2, you are much more interested in whether beta 2 might in fact be larger than the hypothesized value of beta 2. And in this case, this equality effectively means less than or equal to. Then in the third column for the left-tailed test, we'll use this specification as an alternative hypothesis if you are particularly interested in whether the true beta 2 is less than or equal to some specified value for beta 2. Okay, and then the rest of the steps follow similarly for each type of test, whether it's two-sided, right-tailed, or left-tailed. Steps 2 to 5 are effectively the same. One important thing that I'll highlight here is that when you look up a critical value in the t distribution table, you should just put a negative sign in front of the value when you're dealing with a left-tailed test, right? So if you look at the t distribution table, you'll notice that there are no negative values given in this table. And that is because this table only gives values for the right side of the t distribution. And it does that because the distribution is symmetric. If you want to find a critical value associated with a probability of 0.05 in the left tail of this distribution, then it would be equal, the absolute value of that critical value will be equal to the critical value had it been on the right side of the distribution, right? But you just have to put a negative sign in front of the number. In the example given on the table here, in this picture given above the table, here it tells you that the critical value for a right-tailed test associated with a significance level of 0.05 is 1.725. Okay, if you wanted to look up a critical value associated with a significance level of 0.05 in the left tail, it would still be 1.725, except it would be minus 1.725 in that case. Okay, so the value would lie to the left of 0 and it would be negative 1.725. So if you're dealing with a left-tail test, please just put a negative sign in front of the critical value that you've found in the t distribution table. So do consult this table if you're unsure of anything related to hypothesis testing for beta 1 and beta 2. Again, here, degrees of freedom are given by n minus k, as was the case for the confidence interval estimation. So again, this is just the sample size minus 2. It will always be 2 because we are dealing with bivariate regression. We're estimating 2 parameters. So there's 2 degrees of freedom. So just be mindful of that as well when looking up the critical values. All right, so the table on this slide tells us about the 2 types of errors that occur when doing hypothesis testing. We call these conveniently a type 1 error and a type 2 error. A type 1 error is when a null hypothesis that is true gets rejected. On the other hand, a type 2 error is when a false null hypothesis is not rejected. And I should just note that there appears to be an error on this slide. Okay, I'll get to the error in a moment. But it turns out that the significance level given by alpha is the probability of committing a type 1 error, right? Probability of a type 1 error. And so that's an interesting thing to note, because it tells us that if we want to reduce the probability of committing a type 1 error, we simply choose a lower significance level, right? And conventionally, we choose significance levels of 0.05 or 0.01. Okay, so that tells us there's a 5% or 0.5 probability, or 0.05 probability, or 0.01 probability of committing a type 1 error if we choose those significance levels. And you might be asking, well, why don't we just choose an even smaller significance level than that? And the reason why is because it turns out that there is a trade-off between committing a type 1 error, between the probability of committing a type 1 error and the probability of committing a type 2 error, which gets me to the error on this slide. 1 minus alpha should actually be over here, right? Because that is the probability of not committing a type 1 error. That is when we have a true null hypothesis and we do not reject that true null hypothesis. So that's no error. And the probability of that outcome would be 1 minus alpha. So the probability of committing a type 2 error is in fact given by some value beta. But what is important to note is that there is this trade-off between committing a type 1 error and a type 2 error. And it's easy to see this when it's illustrated graphically. So recall when we are stating our 2 hypotheses, we have a null hypothesis where beta 2 is equal to some specified or hypothesized value for beta 2, call that beta 2 star. Often it's 0, but it can be any value. And then let's make it a right-tail test as the alternative hypothesis. We might have, we'll in that case have beta 2 is larger than beta 2 star, right? So imagine this is the test that we're running. So graphically, we can depict this situation as follows, and I'm going to keep it as sort of abstract as possible. And let's say that we are doing this test at significance level alpha equals 0.05. If the mean value of this distribution is given by beta 2 star, in other words, what we're saying is that the null hypothesis is true, and this distribution is the sampling distribution of beta 2 hat. again means that the expected value of beta 2 hat in this case is beta 2 star, so therefore it's an unbiased estimator. If this null hypothesis is true, when we sample from this distribution, whatever the data may be, and we estimate regression models, we will have a 5% chance of drawing a sample that gives us some value for beta 2 that lies this distance from beta 2 star, if beta 2 star is in fact true. And the actual value given by this sampling distribution will of course depend on the degrees of freedom as well as the significance level which we've chosen as 0.05, but let's not worry too much about that at this point. Let's just call this value A over here. If beta 2 star is true, there's a 5% chance that we are going to draw a sample of data, run a regression, and find a value for beta 2 hat that lies to the right of A in the sampling distribution here. The statistic, of course, that is. The statistic being beta 2 hat minus beta 2 star divided by the standard error of beta 2 hat, right? There's a 5% chance that this statistic is going to lie to the right over here, okay? Which would, if that is the case, it would force us to reject the hypothesis that that beta 2 is in fact equal to beta 2 star. Now, what if the null hypothesis is untrue and beta 2 is in fact larger than beta 2 star? In that case, the true beta 2 is going to lie somewhere to the right. Right, let's just put it here for argument's sake. And the sampling distribution of this statistic is going to lie somewhere to the right as well. Right, and if we select a significance level of 0.05, which is associated with a critical value of A in this case, then that's going to give us a value over here. And although A is associated with a 0.05 probability for the distribution on the left, which would be the correct distribution if beta 2 is in fact equal to beta 2 star, if it is the case that beta 2 is larger than beta 2 star, then the probability associated with making the type 2 error will be given by this area over here, which may be larger than 0.05. In other words, have a higher probability. But more importantly, look at what happens when we choose a significance level that is smaller than 0.05. In other words, look what happens when we try to reduce the probability of committing a type 1 error. Now notice the black area in this graph gives us the probability of a type 1 error, which is in this case 0.05. The red probability is beta, and that equals the probability of committing a type 2 error. Okay. Recall that a type 2 error is when we fail to reject a false null hypothesis. Okay. So if we should reduce alpha, let's choose a blue color over here. Should we try to reduce alpha to some value less than 0.05, then it's going to lie somewhere over here. In that case, we reduce the probability of committing a type 1 error, but we necessarily increase the probability. Let's make this green here, or let's continue with the red. Increase the probability of committing a type 2 error. Okay, and that's why there is a trade-off between committing a type 1 error and a type 2 error. So choosing an alpha level matters, right? A level of significance. You cannot arbitrarily just decide, okay, I'm going to choose an alpha level that is as small as possible because that reduces the probability of committing a type 1 error. It might be consequential if by doing so you are raising the probability of committing a type 2 error. Depending on what the model is that you are testing, this can matter quite a lot. Sometimes it's very important that type 1 error is avoided, right? And sometimes it's much more important that a type 2 error is avoided. That is, that you have a null hypothesis that is in fact false, but you do not reject it. And you can see why this might matter in something like, for example, a drug trial. Okay, now let's look at an example of doing an hypothesis test. This is looking at one of the previous regressions where we had a final mark for a course regressed on lecture attendance, and we estimated a beta 2 hat estimate of 2.2811, and we're testing the hypothesis that beta 2 equals 0 against the hypothesis that beta 2 is larger than 0. So this is a right-tail test. So step 1, we state the hypothesis. Null hypothesis is beta 2 is 0. The alternative hypothesis is that beta 2 is larger than 0. And step 2 involves calculating a test statistic. So again, we just use this statistic given over here. We substitute the values, beta 2 hat being the estimate that we estimated. In this case, the hypothesized value for beta 2 is 0. So it's 2.2811 minus 0. And we divide that by the standard error for beta 2, which is given in the table. And when we simplify, we obtain a test statistic of 10.03113122. Then in step 3, we look up the critical value. And to do that, we go to t-table. In this case, we had a sample of 42, I believe. So the degrees of freedom is 40. And we are doing a right-tail test at significance level 0.05, that is, right? Alpha equals 0.05 in this case. So we are interested in this column over here where we have 0.05 as the smaller value in the header. And we're interested in 40 degrees of freedom, and that is associated with a critical value of 1.684, which is what's given on the slide as well, over here, 1.684. And clearly, 10.03122 is greater than 1.684, and therefore the null hypothesis is rejected. Graphically, what that would look like would be something like this. All right, so this would be the sampling distribution. We have 0 over here, the t distribution. The critical value we looked up was 1.6. I'll just write that at the bottom here, 1.684, which means that anything to the right of that forms the rejection region, right? That the area of the sampling distribution to the right of 1.684 makes up the rejection region. And clearly, a value of 10 lies much further than that to the right. Okay, so it lies within the rejection region. So we reject the null hypothesis that beta 2 equals 0. And what does this mean? The alternative hypothesis is favored in this case. And what that suggests is that there is a benefit to attending lectures, right? If lecture attendance increases, then on average there is a positive increase in the final mark for the course. So even though we had a small r squared for this model, there's nonetheless a positive. We do not reject the null hypothesis that there's no relationship between lecture attendance and course mark. All right. Of course, we can argue about whether this is a good model for final marks. Many other things influence marks other than lecture attendance, but given that we are dealing with simple bivariate regression in this course, that we are restricting our models to single explanatory variables. Okay, so we can also do hypothesis testing on the variance of the error terms, but we won't get into that now. I think we will cover the last part of these slides in a separate video.